I wonder what I got in my rotational motion test. Come in. Hey, what's up, John Tannis, Mr. Taylor here. I have your rotational motion test. Not sure why I'm exactly inside your house, but that's none of my business. Alright? You got a pretty good grade in the test, you know? It's a 0. You missed everything, you suck. What the heck? I got a 0. I freaking suck at rotational motion. I really do suck at rotational motion. I should probably look on the internet how to get better. Wait, did I hear someone saying something about someone sucking at rotational motion? I got you. I'm a rotational motion god. Me and my 2 friends, Mr. Wiggles here, gonna help you out learn this material.
Wait, what the heck? How did you get in my closet?
Don't worry about it.
Alright,
Yeah.
I guess I'll just listen to you.
Out of everything on the rotational motion test, torque was the hardest.
Oh, you don't know what torque is?
Whoa!
Whoa.
Torque How'd you get in my car?
Alright, torque is how effective a force is at making an object spin, or, in other words, accelerate rotationally.
Alright. Like, I understand the equation is force times radius sine theta, but I don't really know how to work that equation.
Well, the first part of the equation, r, the r stands for radius, the distance the force is from the axis of rotation.
And what does the F stand for?
The F stands for force.
And what about the sine theta?
The sine theta stands for the sine of the angle that the force is applied. That is why when the force is applied perpendicularly, it's the maximum torque.
Oh, makes sense. If only there was some person, some magical person, to show me an example of torque. What about me? So, Mr. Claus, how exactly are you going to show me an example of torque? How does you spinning the basketball apply to the torque equation?
Well, the radius is the distance from my force to my finger.
And what about the F part of the equation?
Well, that's the force I'm applying to the basketball constantly.
Okay, what about the sine theta?
The sine theta is the angle at which I'm applying this force to the ball, which is near perpendicular, leading to a greater torque.
Oh, Miss Piggy, I'm so glad I understand torque now, but what am I going to do about moment of inertia?
Oh my gosh, how do you not know what moment of inertia is? Do you know what inertia is?
Yeah?
Well, it's the same thing, except it's an object's tendency to resist angular acceleration.
So now that I know what moment of inertia is, how would I solve the moment of inertia for a basketball?
Well, you see, that basketball is a hollow sphere, so that means the moment of inertia of that basketball equals 2/3 mr squared.
Alright. Well, how would I solve for the moment of inertia for this filled disc?
Well, that filled disk you have there has a separate equation for its moment of inertia. The equation is 1/2 mr squared. The m stands for mass, and the r stands for the radius in both equations.
So what effect does the object's shape have on its moment of inertia?
Well, let's take a look at this hollow cylinder and this filled cylinder. Well, they both have the same mass and the same radius, so let's look at the equations and see how it affects its moment of inertia. For a hollow cylinder, the equation is I equals mr squared. For a solid cylinder, the equation equals I equals 1/2 mr squared. So, if the mass is 2.3 kilograms for the hollow cylinder and its radius is 0.1 meters, its moment of inertia should equal 0.023. For the solid cylinder, the mass and the radius are the same thing, except at the beginning of the equation there's a 1/2. So I equals 1/2 2.3 times 0.1 squared, and the moment of inertia equals 0.0115, which means that the solid cylinder has a smaller moment of inertia.
So I understand torque and I understand moment of inertia, but what about angular momentum? I don't understand that.
Well, you know what linear momentum is, right?
Yeah, how strong an object moves.
So basically, angular momentum is how strong an object spins.
So, what's the equation for angular momentum?
The equation is L equals IW.
Okay, what does the I stand for?
The I stands for the moment of inertia.
Okay, and I know how we find that because you just taught that to me, but what does the W stand for?
The W stands for angular velocity.
Okay, so is angular momentum conserved like linear momentum?
So suppose Ronak is an ice skater that is spinning. He wants to increase his angular velocity, but he doesn't know how. Ronak, you should bring in your arms. Alright? Now he's spinning a lot faster than he was before. That's because his moment of inertia lowered, which led to an increase in angular velocity.
Kinematics was actually one of my better parts on the test, so I think I'm actually going to teach rotational kinematics to this guy. Alright, John Ted, you better give me a good grade in this rotational kinematics test. Last time you taught me physics, I ended up getting a 42 while Shion got a 100, and that just made me cry for quite a while. So now you want to learn rotational kinematics. Basically, linear kinematics, you should already have the equations from earlier this year. And rotational kinematics, what you basically do is you exchange for every v variable you have, you exchange it with a w for rotational kinematics, and for every acceleration variable you have in a linear equation, you exchange it with an alpha variable in the rotational kinematics. And every single delta x, which is changing x, you exchange that variable with theta. Alright, thanks to all those kinematic equations you've given me, I think I can use them to solve this quagmire I have in my real life. So basically, I have this dumbbell, and this plate is rotating with an acceleration of 3 radians per second squared. And I was just wondering, after 4 seconds, what will the angular velocity be?
So in your quagmire here, you said that the dumbbell accelerated at a speed of 3 radians per second squared, right? Okay, and you also said that you wanted to find out the speed after 4 seconds, so you have 4 seconds. Alright, so in the equation, you're trying to find the end velocity, okay? So since it starts at rest, your initial velocity will be 0, so you plug in 0, and then you plus, and then now you have the acceleration, so which would be 3, and then you have the time, which would be 4, so you find that the end velocity will be 12 radians per second.
Alright, thanks for teaching me how to use rotational kinematics. Now I know how to just plug in my variables and solve my unknown. It's actually pretty similar to linear kinematics. I'm pretty sure I did well in that test. Come in. Hey, what's up, John Ken? This is Taylor here. Still not sure why I'm in your house, but got your rotational motion test, and I had to say, you have some pretty good tutors. Got 100. Yeah, I love rotational motion. Talk if you need to, but I can't stay to hear you. That's the wrong thing to do.